So, using JLab data combined with the SLAC data suggests a proton made of 9 pions, presumably 5 positive pions and 4 negative pions. This begs the question, what is the HERA data showing? Shown is a combined plot of the SLAC, HERA, and JLab datasets using a logarithmic x-axis. The SLAC points are raw data points, but the HERA and JLab values are rough estimates of the average F2 for a given x from a phenomenon known as Bjorkane scaling. Bjorkane scaling occurs when F2 stays fairly constant over a range of q² values for a given x, indicating the probing electrons are scattering off particles inside the proton. The combined F2 graph reveals 2 interesting things. 1, the 3 data sets converge at x equals 1/9, and 2, the HERA curve has the same shape as the SLAC curve, just at higher F2 values over a tighter momentum fraction range. It can be shown that the HERA curve is likely the F2 structure function curve of the particles inside the proton, the pions, sitting on top of the proton F2 curve. The wavelength of the probing electrons in units of Fermi, 10 to the minus 15 meters, is approximately equal to 1 over the square root of the q² of the collision. The high q² of the HERA collisions make its probing electron wavelengths much shorter than the electron wavelengths of the lower q² collisions of SLAC and JLab. This allows the HERA electrons to focus in on much smaller structures within the proton. If there are structures within the pions, the HERA electrons can likely see them. Scaling the momentum fraction of the HERA curve so that a proton momentum fraction of 1/9 is 1 on the new pion curve, and subtracting the proton F2 value at x equals 1/9, about 0.36, from the HERA F2 values of the curve to adjust the proton F2 value at x equals 1/9 to 0 to represent a whole pion, creates the pion F2 curve. Restoring the x-axis to a linear scale and zooming in on the region of the curve containing the peak gives the curve shown. Analysis of this new pion F2 curve reveals that it peaks at around x equals 0.0049, or about 1/204th of the pion's momentum. This means that on average, there are 204 particles in each of the pions in the proton. If there are 9 pions in a proton, this suggests that the proton is made of about 1,836 of the pion component particles, and the pion is made of particles that are about 1/1,836th the mass of the proton. Since the mass of the proton is 1,836.15 times that of the electron, it appears that the pions inside the proton are made of particles similar in mass and likely charge to electrons and positrons. Call them beta electrons and beta positrons to distinguish them from the free electrons and free positrons typically observed in nature. For the proton made of electrons and positrons to have a positive charge, there must be one more positron than electron, making the total number of particles odd. So, if the proton's mass is equivalent to 1,836 free electron masses, it is likely made of either 1,835 or 1,837 beta electrons and positrons. This model assumes 1,837 so that a free electron has something extra about it that distinguishes it from the beta electron. That makes a proton 919 beta positrons and 918 beta electrons. With 1,837 particles making up the proton, each beta electron and beta positron in the proton is slightly less massive than a free electron, since it only takes 1,836 free electrons to make a proton. So, where does the free electron get its extra mass, and how is it different from the beta electron in the proton? In this model, the free electron differs from the beta electron in that it is a beta electron coupled with an electron neutrino. The neutrino gives the free electron its extra mass. The free positron is a beta positron coupled with an electron antineutrino. A proton with a mass of 1,836.153 free electron masses that is made of 1,837 beta electrons and beta positrons makes the mass of a beta electron and beta positron 0.99954 times the mass of a free electron. This implies the electron neutrino adds about 0.00046 free electron masses, or 235 eV, to the mass of the beta electron to form the free electron. This is slightly greater than the current electron neutrino mass upper limit estimate of about 2 eV. Our model of the free electron is a so-called beta electron coupled with an electron neutrino. So how do these two particles come together to form the free electron? The electron magnetic moment may provide the answer to this question. Ideally, the Bohr magneton, the charge of the electron times Planck's constant divided by 2 times the electron mass, should be the magnetic moment of the electron. However, it differs slightly from the measured electron magnetic moment by the so-called electron anomalous magnetic moment, which is 0.0011596. While contemporary particle physics offers a different explanation for this difference, the anomalous magnetic moment may actually provide insight into the structure of the free electron. It can be shown that putting a beta electron in the right orbit around an electron neutrino can correct the Bohr magneton approximation of the electron magnetic moment to the measured value. In a wire loop, the magnetic moment is the electric current flowing through the loop in coulombs per second times the area of the loop in meters squared, producing a quantity with units coulombs meters squared per second. For the magnetic moment of a spinning charged particle, these units more likely result from the moment of charge of the particle, coulombs meters squared, times the particle's frequency of rotation, reciprocal seconds. Here, the particle's moment of charge is the charge analogy of its moment of inertia, replacing the mass of the particle in the inertia expression with its charge. The classical radius of a free electron, 2.82 times 10 to the minus 15 meters, is more than 3 times the 0.85 times 10 to the minus 15 meter radius of a proton. So, even though the proton's mass of 1.67 times 10 to the minus 27 kilograms is more than 1,800 times the electron mass of 9.11 times 10 to the minus 31 kilograms, the electron's volume of 9.4 times 10 to the minus 44 meters cubed is more than 36 times the proton volume of 2.6 times 10 to the minus 45 meters cubed. This makes the average density of the electron 9.7 times 10 to the 12th kilograms per meter cubed, 67,000 times smaller than the proton's density of 6.5 times 10 to the 17th kilograms per meters cubed. Assuming the density of matter that makes up all subatomic particles is constant, that is, the matter cannot be concentrated or diluted, and for simplicity, that the proton is essentially solid subatomic matter, for the matter forming the electron to retain the proton density with the assumed electron radius, it would have to configure itself in a hollow sphere with a very thin shell. If the electron density is equal to the proton density of 6.5 times 10 to the 17th kilograms per meters cubed, since its mass is 9.11 times 10 to the minus 31 kilograms, then the volume its mass occupies, the electron's material volume, is its mass divided by the proton density, which is 1.4 times 10 to the minus 48 meters cubed. If the electron is a sphere with a radius of 2.82 times 10 to the minus 15 meters, then its mass must cover a surface area of 4 pi times that radius squared, or 1.0 times 10 to the minus 28 meters squared. To retain a material volume of 1.4 times 10 to the minus 48 meters cubed, while covering a surface area of 1.0 times 10 to the minus 28 meters squared, the electron mass must form a hollow sphere with a wall thickness delta R equal to the electron material volume divided by its surface area, or 1.4 times 10 to the minus 20 meters. This would make its moment of charge 2/3 its charge Q sub E times its radius R sub E squared, replacing the mass in the hollow sphere moment of inertia formula with charge. Now, the electron magnetic moment becomes 2/3 the electron charge Q sub E times its radius R sub E squared times its frequency of rotation nu, the Bohr magneton, which produces a value slightly less than the measured magnetic moment. However, if the beta electron is assumed to be a solid sphere with a radius much smaller than the free electron, it can assume a high-speed orbit around an electron neutrino to form a model of the free electron that produces the measured electron magnetic moment. The high-speed orbit creates a virtual ring around the electron neutrino with a radius equal to the electron radius. That ring precesses about an axis through the central electron neutrino, producing a virtual hollow sphere around the neutrino. Applying the parallel axis theorem to determine the moment of charge of the orbiting beta electron precessing about the electron's central axis, which for a charged body with respect to an axis not through the body is the moment of charge of the body, plus the charge of the body times the average distance squared it is from the axis. The moment of charge of the free electron system is the moment of charge of the solid spherical beta electron orbiting the neutrino, 2/5 Q sub beta R sub beta squared, plus its charge times the average distance squared its orbit is from the axis about which the orbit precesses, Q sub beta times d bar squared. Assuming the beta electron is in a circular orbit around the neutrino for simplicity, d bar squared works out to be 2/3 R sub E squared. So the parallel axis adjustment to the beta electron moment of charge, Q sub beta times d bar squared, is 2/3 Q sub beta R sub E squared. This makes the moment of charge of the beta electron 2/5 Q sub beta R sub beta squared plus 2/3 Q sub beta R sub E squared, and its magnetic moment this quantity times its frequency nu. The moment of charge can be expressed as the quantity 1 plus 3/5 R sub beta squared over R sub E squared times the quantity 2/3 Q sub beta times R sub E squared. Since Q sub beta equals Q sub E, the moment of charge can be written as the quantity 1 plus 3/5 R sub beta squared over R sub E squared times the quantity 2/3 Q sub E R sub E squared. Multiplying 2/3 Q sub E R sub E squared times nu produces the Bohr magneton. Now, the quantity 1 plus 3/5 R sub beta squared over R sub E squared appears to correct the Bohr magneton to the actual electron magnetic moment, making it equal to 1 plus the anomalous magnetic moment, where 3/5 R sub beta squared over R sub E squared becomes the electron anomalous magnetic moment 0.0011596. From this, it appears the radius of a free electron is about 23 times the radius of a beta electron. The anomalous magnetic moment indicates that the free electron is not a thin-shelled hollow sphere, but a beta electron in a high-speed precessing orbit about a central electron neutrino with a radius about 23 times the radius of the beta electron. The pions in our proton model contain, on average, 204 beta particles, 102 beta electrons, and 102 beta positrons, yet each still carries a charge. This configuration can be accomplished if the negative pions contain 101 beta positrons, giving them 203 betas and a -1 charge, and the positive pions 103 beta positrons, giving them 205 betas and a +1 charge. This gives the proton 1,837 betas that average 204.11 betas per pion. The relatively blunt proton F2 curve, with a peak of about 0.36, much less than 1, indicates that the pions that make up the proton interact strongly with each other. That is, they are likely a somewhat tightly bound cluster within the proton. The mass of a free charged pion is 139.57 MeV, or 273.18 free electron masses, likely making the free pion 273 betas. This makes the average mass defect of a pion within the proton 69 beta particles, or 39.25 MeV, and the total mass defect of the proton about 620 beta particles, or about 317 MeV. This is nearly 12 times the 28.3 MeV mass defect of the alpha particle. The pions are tightly bound within the proton. The sharp peak of the pion F2 curve, near an F2 of 1, says that the beta electrons and beta positrons forming the pions do not interact strongly with each other. Because of this, they are likely in an orbital-like configuration within the pions. This is probably why there is virtually no mass defect between the beta electrons and beta positrons in the pion and those in the free electron and free positron. The assumption is that two pions bind together because when they collide, beta electrons and beta positrons from the two pions annihilate each other, leaving each pion with a beta deficit. To fill that deficit, the two pions share beta electrons and beta positrons between them to feel whole. The pion collisions that formed the proton were extremely strong, and many beta electrons and beta positrons were annihilated. This resulted in each pion within the proton sharing a total of 69 beta electrons and beta positrons with the neighbors it binds with. When two protons collide, a pion from each proton collides, annihilating some beta electrons and beta positrons from each. However, because the pion collisions that bind protons are not nearly as strong as those that formed protons, there are not 69 betas annihilated, but 4 to 6. The two pions then share the deficit number of beta particles, forming a bond between them and a bond between the protons of 2 to 3 MeV. We now have new models of the electron, the positron, and the proton. More comprehensive analysis of the electron-proton deep inelastic scattering data reveal the proton is likely made of 9 pions, and those pions made of particles we named beta electrons and beta positrons. The beta electrons and beta positrons are slightly less massive than free electrons and free positrons, and appear to be the proton's most basic component particles. The beta electron couples with and orbits an electron neutrino to form a free electron, and the beta positron an electron antineutrino to form a free positron. The radius of the free electron is about 23 times that of the beta electron. Our proton is made of 1,837 particles, 918 beta electrons and 919 beta positrons that arrange themselves into 5 positive pions and 4 negative pions that have an average bound mass of about 204 free electron masses each. Though not discussed here, the neutron is modeled as an extension of the proton, having 2 extra beta electrons and 1 extra beta positron, giving it 920 beta electrons and 920 beta positrons and a charge of 0. Using these models, we can explore how atoms see neutrinos.